You can start now. So, there is a small topic on torsion that I will cover, and then I will stop as far as torsion is concerned. Torsion, this is a, supposing you have a shaft and then it is applied a distributed torque along the length of this. Distributed torque is there, not fixed torque, which was there. So, distributed torque means, let us say it is called, it is mz per unit length. Torsion distributed. How will you formulate this? So, now the situation is like this. If I take a small length of dz, this is not total length, dz only. There will be, as you are moving along the length, there will be, and this cross section and this cross section will have different torques. So, this cross section will have a T, and this will have T plus delta T. T is not uniform throughout. This is only difference, So, how will you formulate this problem? How will you formulation for this? I must have, this is not given in standard text, but I also, not that I have invented this problem, I must have seen in some book or somewhere. So, I have got some notes here. How will you formulate this? You are applying, yes, a torque. So, now you have this, see, you have this formula that T equal to G j theta. I told you equivalent, G j theta, and theta can also be written as G j multiplied by theta. Theta is per unit length. So, if angle of twist is, because here the angle of, if angle of twist is alpha, so it is d alpha by dz per unit length now. So, this will be, alpha is angle of twist and theta is angle of twist per unit length. So, theta is replaced by this. So, I have got one formula, if it is varying, yes, and then here if this length is dz, so equilibrium is maintained. If you see here, equilibrium delta t, net torque is equal to delta t, t plus delta t. So, delta t plus mz into delta z. This is per unit length. So, this plus the difference will give me 0, and therefore, as dz tends to 0, yes, dz tends to 0, I can write this as and dt by dz equal to mz minus with a minus sign. Dt by dz equal to this. This is my second equation. So, these are the two operating equations. These are the two equations. Now, I can get one equation out of these two. One can get one equation out of the above two. How will you get? D upon dz dt, na? T is given by, so I can substitute in this T. So, d upon dz and the value of T gj into d alpha by dz equal to minus mz. Mz is the distributed torque applied along the length of the shaft. If so, this is your governing equation. So, this is the governing equation. Even if Gj is varying, it can be like this, and if Gj is constant, then you can write down Gj d square alpha by dz square second derivative equal to minus mz. What I want to tell you is that second order equation in alpha we have got. Alpha is the angle of twist. So, this is the governing equation in alpha. You see, similar equation we also get if you have distributed load along the length of a rod. There also you get AE d square u by dx square equal to distributed load P, second order. So, it has a similar form. Instead of alpha it becomes u. So, many problems in mechanics have similar form. If you go to heat conduction problem also has a similar form. Conduction of heat in a conducting body. I mean, if you heat a body, how does heat flow inside? That is also governed by a simple second order differential equation. So, the basic idea what I want to tell you, that if you know how to solve one type of equation, you can solve the other problem also. Okay. Now, there is an alternative formulation. This is a single governing equation, single. It is the governing equation. In single variable alpha. Now, this second order equation can also be written. I told you, see, if you standardize your method of solution, standardize means, yes, you know how to solve a system of first order equation, which is also called state variable. Which I also explained. I mean, I have been explaining that you can write down your equation in first order form. So, this an alternative form of torsion equation as first order equation, as see second order equation cannot be directly integrated by numerical integration. Numerical integration method that you have learnt in numerical analysis like Runge-Kutta method, Euler's method is only for first order ordinary differential equation, not for second order. So, you have to, if you want to use one of those techniques to integrate your equation, you have to transform this into first order. So, either two equation 1 and 2 can be written in provided if you have dz by, see we already have one, I think initially also I gave you two form, but does not matter. So, we already have this t equal to, for example, t equal to g into j into d alpha by dz. So, this itself can be taken as it is. I can write 1 d alpha by dz equal to t by gj as one equation. And second equation I can write which came directly from my the dt by dz, dt by dz equal to minus mz. So, this one now instead of one variable alpha, now we are having two variables alpha and t, and I can write down this into a simultaneous equation in matrix form alpha and t So, the form of this equation is again in the standard form which we have been discussing. This can be called y, a y vector of two variables equal to this matrix is my A or B matrix, it is a B matrix which I call it. This is y plus this is my load q. So, it is a coupled first order ordinary. So, this is a coupled first order. So, I have explained the same thing for 3 dimensional as well as for 2 dimensional problems. So, it is a set of, that is the above is a set of two first order coupled. Why it is called coupled, not uncoupled? Because t and alpha are related to each other. there is something is they cannot be coupled. ODEs, ordinary differential equations. By the way, y is also called a state variable. State along the path, these are my variables which I have to find out. So, this is state variable. So, this is what I just wanted to tell you, that this formulation also now can be. So, torsion of non-circular section is an application of three-dimensional theory of velocity. It so turns out that the problem turns out to be a two-dimensional one. Instead of 3 dimension, it turns out to be a 2 dimension. But it is exact solution. So, if you can solve this, you will get exact solution of torsion. So, this is one part. Now, see so far we have been formulating all our problems in terms of rectangular Cartesian system of coordinate x, y, z. That means, the geometry of my problem also has to be in the same rectangular, everything rectangular, but in nature everything is not rectangular. Some are elliptic, some are parabolic, some are circular, cylinder. There are so many geometries that you get in nature. How will you solve such problems? Solid does not mean only rectangular coordinate x, y, z, that you can define your geometry in x, y, z. So, some coordinate system that you are aware with, that like cylindrical coordinate system r, theta, z. You have r, you have theta, and then z. You can get a cylinder. So, that gives you cylindrical surfaces, cylindrical solids, and we can derive all your equations in cylindrical coordinate. Then you also have sometimes spherical, a ball, spherical football. So, there also you have r, theta, and phi. Instead of r, theta, z, I think you must have done also r, theta, phi, spherical coordinate system. So, you can get a spherical bodies, solids, but I have not elliptical coordinate system. Have you heard about? Parabolic coordinate system, no. But then you do get surfaces, solids made out of this parabola. So, one has to deal with all such geometries. So, best thing would be to write down your theory of velocity equations in what is called orthogonal curvilinear coordinates, where there are 3 coordinate system alpha, alpha 1, alpha 2, and then there is a third one also. At every point they are all orthogonal to each other. Now, they need not be orthogonal. There are some people, some scientists have also derived equations of elasticity equations in non-orthogonal coordinate system. It becomes very complex, because once you say 90 degrees, then some simplification has to arise. So there are some special geometry that you can create out of non-orthogonal coordinate system. One simple example is, you must have, do you know skew plates? Plates, this is a plate. If it is supported and then loads are applied transverse, so it is a plate. So, normally you have your culverts, bridges, they are generally right angle. River is flowing and you have this shore, so you support it. But sometimes the road is, this is the river and road is inclined to this. So, you have to have a inclined. So, your plate will not be having 90 degrees, but it will be, two angles will be more than 90, two angles will be less than 90. So, that geometry is called skew plate, skew. So, that is a very common, skew plate is very common occurrence in practice, especially when it comes to culverts and bridges. Skew angle. So, if skew angle is 90 degrees, then it is rectangular. If it is 0, of course, you cannot have 0, but as you go smaller and smaller, complications go on increasing. So, one way is to derive equations for each one of these separately. There is a book only on skew coordinates, skew plates. One person decided to write only skew, where angle is not 90 degree. One British designer, his name is Morley, Morley, Morley. So, there is a skew plate, the title of the book is there in our library, skew plates. So, if you want to study skew plates, then you will have to refer to the equations derived by Morley. And theory of velocity for cylindrical coordinate system, for spherical coordinate system, you see one can derive from basics by taking the element, just like we have taken a small element in rectangular coordinate in Cartesian x, y, z, you take one small element in cylindrical coordinate system r, theta, z, and consider that, and then you can derive. Similarly, in spherical coordinate, again you can derive. So, this is one alternative, but the best alternative is to derive the equations in orthogonal coordinate system, curvilinear orthogonal coordinate system. So, actually in the past I used to give once in a while one assignment for people to this class to derive theory of velocity equations in orthogonal curvilinear coordinates. There are some scientists who have worked very hard, not that they have become obscure, these things are useful. Sometimes when you have to, you have got a geometry which is not, doesn't fit into rectangle, then you will have to. So, there is a book written about 50-60 years ago, it is by Morse and Feshbach, Mathematical Methods, Morse and Feshbach, Feshbach, Feshbach. It is there, volume 1 and volume 2. There are 2 volumes. Mathematical methods in physics. See, physics and engineering more or less similar problems we encounter in general physics. So, mathematical methods in physics. So, that book discusses a lot about curvilinear coordinates. So, when you have now, I have not given this year any assignment to you to derive. So, if you get time, please read. In fact, when I was a student, my teacher, he asked each one of us to derive in a particular, there are so many types, if you take that book, there are so many names like elliptical coordinate system, parabolic coordinate system, some other coordinate. So, he had asked us, each one of us, to derive the equations in one of those coordinate systems, one. But if you know the general one, it is the best. And if you know the general, then the theory of theory of shells becomes easy. You have to know this. Theory of shells is dependent on curvilinear coordinate system. So, when you study next course, that is theory of shells and plates, there it becomes life becomes easier. So, that is as far as your, I mean, I am telling you, this is only on your self study, I am not asking you to do it. But then I have got here some derivations which I have done, which I would like to share with you. In two dimensional 2D, what is the most popular non Cartesian system of coordinate? Polar coordinate system. There is only one polar, r theta. So, there is a book again, and if you want, I have got a if you want it, I have got what you call e-copy of this book. So, by M. Amin computational elasticity. Now, he has derived, I mean, this is the title is two dimensional problems in elasticity, but then afterwards here two dimensional problems in polar coordinates. So, r theta. So, your element becomes your basic element, instead of x and y dx dy, it becomes this, that is r d theta and dr, size become dr, and then this is how you will have to consider, and you will have to derive all these equations in. This is the simplest, what I am saying, this is the simplest. You take just polar coordinate 2 dimensions, so at least you will get a feeling of how it is derived. So, all these are derived because you have to at least some simple problems of circular geometry, thick circular plate, supposing I want to solve it, how will I solve it? Not by whatever we have done, we will have to do it again. So, please see the equations derived in polar coordinate. This is a part of your course. This is one polar coordinates, and then so quickly let me then, because first I wanted to start with 3 dimensional, that is cylindrical coordinate system. This is plane cylinder. This one is plane elasticity problem in cylindrical coordinate, because this is a special case of 3 dimensional. So, I have that one is complete, about 20-30 pages was there. Yes, it was there. So, elasticity equations is cylindrical coordinate. Okay. So, this is another important. So, you have r theta, I mean this is x y z, you have r, and then if this is the point, so theta is this direction and z will be perpendicular to this in z direction, and this is the kind of element that we are talking of, that will be there in r theta z direction. So, you will have to kindly, I mean this you will have to make some special effort. So, I will quickly go through it. Then I have taken here a projection z equal to constant. See here these normal, see this, what is important here is this is r direction is inclined. So, normal to this will not be in a particular direction, I know. So, this normal, it is here and this normal is here, they are not in one line. Yes, in r direction they all the stresses will be in the same line, but not in theta direction. Theta direction, for example, if this is sigma theta, this will be sigma theta plus the increment of theta, sigma theta, increment is this, but direction is not in the same direction, it is not in the same line of action. So, it is, so if you take this is angle is theta, for example, from here to here is theta, so this will be theta by 2 on this side and theta by 2 on this side. So, if you do not take, although this angle is small because we are taking a small element, but then while taking the equilibrium you will have to take cosine and sine, one which will be in r direction, one will be in tangent direction, then only you can take. So, while doing this, so this one you please take precaution. So, this is, then what I have done here is, just for simplicity, I have said, you see, there is also a convention of calling x, y, z as x1, x2, x3, and r is this. So, and these are my unit vectors along x direction is E1, E2 and E3, which we now also call it as I, J, K. You can call it E1, E2, E3. So, here if it is in r direction, so r and theta and z direction. So, I am calling it ER, E theta, Ez direction in the 3. Ez, this Ez and this Ez will be same because z direction will coincide, but not r and. So, all the explanations are given here. For example, what is this? Relation between Cartesian and cylindrical coordinate can easily be written. You can draw the figure. X equal to r cosine theta, this is in polar, and y equal to r sin theta, z equal to z, r equal to under root this, theta equal to this, z equal to this. So, this is another. Now, here I have taken Br, B theta, Bz as the body forces, and then I have tried to find out the, by taking the equilibrium of the element in r theta z direction. See, in r direction, because r has a dimension, r is a coordinate which has got dimension, but theta does not have a dimension, theta is a dimensionless. So, a length in this direction will be r into theta, distance, so that will be the length. So, that is important, So, you have to, when you have to multiply and convert the stress into force, then you have to keep that in mind. It will not be simply like dx dy. So, anyway, you can go through all this, and I will just quickly, this is not there in your quiz, so do not worry, but it is there in your final exam. Derivation, yes. Who says derivations are not there? So, anyway, all these derivations I have done in a longhand. So, completely I have taken the element, I have shown everything. Then the above theta is, if it is assumed is small, tending to 0, such that cosine d theta will become equal to 1, sine d theta will become theta, cosine d theta by 2 again will become 1, sine d theta by 2, because all such things come into the expressions. So, you have to keep this in mind. Then here, by doing all this, finally, one equation of this kind is obtained. If you sum all the forces in r direction, r means radial direction, then you will get one equation of this type. which is equivalent to del sigma x by del x plus del tau yx by del y plus del tau zx by del z plus bx equal to 0. So here it is like this. D sigma r by dr, this by this. These two terms are similar. You have to be careful about this term. This. And then this is another. So please and similarly I have written, similarly we get, it is easily said than done, similarly we always write similarly, but then you have to, supposing I ask you to derive this equation, then you will find. So these three equations, the above are the three equations of equilibrium in cylindrical coordinate. So this becomes cylindrical coordinate, equilibrium equations in cylindrical coordinate. These are the derivations of strain displacement. I have not gone through the derivations. I have just written down here. Here I have also written all the compatibility. Don't write it. All the compatibility equations. And see, constitutive relation, there is no material difference. R theta z is similar instead of x, y, z. So there is no question of dr will not come, d theta will not come, nothing. So this is just exactly. So here there is no. But the other two. Then of course boundary condition either on displacement or on the stresses. So this completes the formulation of boundary value problem in cylindrical coordinates. Now plane stress, I have also put at one place all the equations of plane stress and plane strain in polar coordinates. Polar coordinates means in 2 dimensions, r and theta only. Everything is in xy, r theta in plane. So these are also given here. Stress function slightly takes a change in this. Airy stress function, the final equation will be same, but this one, your del square in polar coordinate. This is del square in 2 dimensional polar coordinate. So polar coordinate you might have done also in mathematics. So this one you kindly keep. And the stresses come, these are the expressions for stresses. generalize Hooke's law, there is no problem, that will be simple. Displacement equations means equation in terms of displacement, or velocity equations in terms of displacement. How will they look like? So for plane stress and for plane strain, I have written here. Okay. And then here I have taken some simple solution for plane stress problem. So this is equilibrium, this is strain displacement. This is compatibility, there is single compatibility relation, constitutive relation. These are the stress values which satisfies equilibrium. That means I am trying to get solution via stress function. That means choose a stress function which satisfies the equilibrium equation. So here it is slightly complex. The form is not as simple. There it was only second derivative of phi with respect to y and second derivative of phi with respect to x plus minus. Here it becomes slightly complicated. This satisfies the equilibrium. What I have done here, yes, because we are using solution, so we are writing compatibility equation in terms of stress function. So we get this one equation which is here. See, it has to be practice, it cannot be. So you have to go through this, and finally this turns out that yes, finally we will get only a del square phi. So final form is same. Biharmonic equation there also we got, here also we get. Only thing is in between complication is more. Now I have taken a thick cylinder. Thick cylinder, axisymmetric problem, internal and external pressure. These are the boundary condition. It is axisymmetric problem, so everything with respect to d upon d theta will become 0. Problem becomes ordinary differential equation only in R. Everything will change only with respect to only R. So it is a one-dimensional problem, axisymmetric. So you get this fourth order ordinary differential equation with variable coefficient, not constant coefficient, but variable coefficient you get here. We don't know how to solve differential equation with variable coefficient. Even ODE, analytical solution with variable coefficient. Numerically I can solve, but not analytically. Analytically it has to have constant coefficient. So what we have done, ODE with variable coefficients have to be converted into ODE with constant coefficient. Change of coordinate system. So let us say psi is equal to log r. I think lot of such things we have studied in our school, how to solve a particular differential. The same thing is done here. And so once you change this, then somehow it turns out to be constant coefficient. So finally with this conversion, if you say psi equal to log r, then it becomes constant coefficient. Yes. So this becomes third derivative, this in psi. These are I have given you, how to get all these derivatives with respect to r. How do you convert that into psi? So these are converted. Then you have substituted into that. If you substitute, we get a. This is my final differential equation in psi, which is a homogeneous ODE with constant coefficient. So this one is solvable. This we can solve. Homogeneous equation goes. But how do you get unique solution of this homogeneous equation? We are solving this circular cylinder with internal pressure and external pressure. This becomes homogeneous. How will you get solution? Homogeneous. I mean, a similar problem is in algebraic equation. Do you have Ax equal to 0, homogeneous algebraic equation? Can it be? Will it give unique solution? No. Here also it will not give unique solution unless you have boundary condition non-homogeneous. Here we are having boundary conditions which are non-homogeneous. Internal boundary P equal to internal pressure, external boundary P equal to external. So these are called non-homogeneous boundary conditions. So homogeneous equation with non-homogeneous boundary condition, you will get unique solution. So that is, so then we get unique solution. So this is what is the final solution. And since this has got these 4 constants can be obtained by the boundary conditions that we have got on the 2. Okay, so final. So it is like this. So it is tedious. What I am saying, it is not easy. But then this you cannot do by just by remembering. Unless you have the book with you complete, then only you can do it. So here you need open notes or open book. Anyway, this gives you the solution. Finally, you substitute the boundary conditions and you will get this constant. So this gives you one way of dealing with. But the best thing is to derive velocity equations in orthogonal coordinates. You can note down, there is a book. I mean, actually you people should search where it is given. In your Morse and Feshbach I have given you. So whenever you have time, you please read. And there is also a book on cells by Novozilov, Novozhilov. Novozilov. Sorry, not Goldenweiser. Novozilov is also Golden Weiser, Weizer, Goldenweiser, theory of cells. And what he derives, his whole book contains equations written for non-orthogonal coordinates. Non-orthogonal. It is very complex. How that he must have spent his at least several years, many decades. But anyway, he has. So if you want to, because with these non-orthogonal, you can get very special geometrical forms. That is only way. And for those you can analyze. So these have some applications. So in olden days, all these works had lot of value. But after numerical and finite element methods etc. have come, people have lost. They don't want to do hard work. Any solid, you fill it with elements. Any solid of any shape and size can always be filled with different kinds of elements, or even same kind of elements. This little approximation, and you can get some approximate solution. But if you want to get exact solution, then you have to take this help of these equations. So this has application. Huh? So okay, so this much I want to say, and today let us close it.